Hello dear friends, welcome to my channel. Today we will be discussing a small topic, fundamental and derived units from chapter Units and Measurements. This chapter gives the importance of measuring the physical quantities and it says us what are the different types of physical quantities and the units. So in our day-to-day life we do measure certain quantities like temperature, current, potential, time, distance, isn't it? So, here a small example I have taken. A person is hitting a ball or kicking a ball, and ball is moving through a distance, and finally getting stopped. So, I can ask many questions like what is the time taken by the ball to stop, what distance it has covered, what is its velocity or speed, what is the acceleration, and all. If we didn't measure, we can't answer these questions, or we will tell that we didn't understand the situation or physical situation properly. If one more person is doing the same activity, and if we want to compare whose ball is moving faster and all, we need to accurately measure, right? So, measuring a quantity is very important. So, to understand the physical situation completely, one needs to measure the physical quantities. So, physical quantities, you all know, from smaller classes onwards, we are studying different physical quantities. Not only what I have mentioned here, there are so many electric car other than these, other than displacement, velocity, acceleration, and all. There are so many physical quantities like current, voltage, energy, different forms of energy, isn't it? Mass, weight, pressure, all these are physical quantities. But here we are to define physical quantities. So we know if somebody asks what are the physical quantities, we can name so many. So what is it? How to define it? So here we will define the physical quantities in this way. That is, the quantities which can be measured directly or indirectly. We do measure time, length, and all directly by using instruments like to measure time, a stopwatch is enough. To measure the length, depends on the magnitude, we do go for the different tools. Meter scale is a one tool to measure the length, isn't it? So indirectly also we do measure, isn't it? To measure the current, we do use a meter. To measure the potential difference, we do use voltmeter and all. Even if without using these tools or instruments also, we can find out by using the formula. That's the meaning of indirectly, isn't it? If we know potential and current, we can calculate resistance indirectly by using this formula, isn't it? If we don't know potential difference, it is not necessary that if what you should have voltmeter right in your hand to calculate the potential difference. We can simply find it from the Ohm's law equation, that is V is equal to IR. From that V, that is the potential difference, we can find. So directly or indirectly means that by using the formula or by directly measuring. So the physical quantities are the quantities which can be measured directly or indirectly, and these are the quantities in terms of which the laws of physics can be expressed. Is any law expressed in terms of physical quantities? So many, right? We have so many examples like Newton's second law, F is equal to ma, universal law of gravitation, isn't it? What is that? G is equal to mm divided by d square. All these laws have been expressed in terms of physical quantities, isn't it? Mass, acceleration, distance, force, all these are physical quantities. So physical quantities we can define in this way. These are the quantities which can be measured directly or indirectly, and in terms of which the laws of physics can be expressed. Process of measuring a physical quantity. What do we need to do first while we measure a physical quantity? I have taken an example. I have a sofa set here. Somebody asked me that what is the length of the sofa. So what should I do first? I need to choose a unit, right? So here I am choosing a convenient unit, or a unit of suitable size, that is meter. And I have a meter scale with me. Now what should I do? I need to check how many times. So meter I fixed. I fixed the unit. Now how many times this meter scale or meter rod will go into this length? That's what I need to check. 1, 2, 3, 4, 4.5 or something. So 4.5 times this meter scale is going inside. Okay, 4 times completely, and next one it is not going half of that. So I will tell them the length of my sofa set is 4.5 meter. This is how I express a physical quantity, or I measure a physical quantity. So first important thing is selection of unit. So I have used here a unit meter. After that, what we need to do? We need to find the number of times that unit is contained in a physical quantity. Here, the physical quantity I used here while measuring the length of the sofa, it is physical quantity being measured as length or distance. So, to measure that, what I did, I have chosen this unit. Then I checked how many number of times or how many times it is going. That unit is going in the given quantity, given length, given physical quantity. Here it is length. So it's going by 4.5 times. So I will tell 4.5 meter. This is how we measure physical quantities. Next is unit. We all know about units. We know that when we express a physical quantity, we need to have units, isn't it? So what are the units? How to define? Units are certain reference standards. It is used to express the physical quantity. So these are the certain reference standards used to express a physical quantity. Now, to get an idea of a physical quantity, we need to do what or how we express a physical quantity. Already I told, but to sum up, first the unit, then the number of times that unit is contained in that. First the selection of unit and the number of times that unit is going or fitting into the given quantity. Next is characteristics of a good unit. There are so many characteristics for a good unit. When do we say that the unit is good? It's fine, it's fair. If it is well defined. What is well defined means? In ancient times, you know that people used handspans to measure the length. Isn't it? Is it a well-defined unit? What do you say? If you have given a table and somebody asks to measure the length and you are using handspan and another person is also standing there near to you and he also is measuring, and you both will be getting a different answer, slightly different answer, because the length of the hand span for individual person, it will be different. It may slightly vary from person to person. So it is not a well-defined, handspan is not a well-defined unit. So when we choose a unit, we should choose a well-defined unit. Then next point is it should be of suitable size. In the previous example of sofa, the measuring the length, I had used a unit called meter. What will happen if I use a unit Fermi? You know, Fermi is a very small unit of length. It is 10 raised to minus 15 meter, isn't it? It doesn't look good if we use a too small or too big unit like astronomical unit or parsec like that. So, when we need to measure something, the unit should be a well-defined one. It should have suitable size. Then it should be easily reproducible. What's the meaning of reproducibility of a unit? That means it should be able to convert or switch from one unit to the other. For example, I'll tell you, when we measure mass, we use kg. 1 kg, we know we can easily switch over it to gram or milligram, like that, isn't it? So that is called a reproducibility of a unit. Reproducible, easily we should be able to switch to other units. That is another characteristics of a good unit. Then next, it should not change with the time. The unit what we took today, it should not change by tomorrow, or it should not change by evening or by after some hours. It should not change with the time. It should not change with the place. It should not change with the physical conditions. What do you mean by physical conditions? Like temperature, pressure, density, humidity, like that. So when we choose a unit, it should not change with the time, place, or physical conditions, and it should be accepted worldwide. It should be accepted internationally. These are the characteristics of good units. Hope it's clear to you. Moving on. Now, the physical quantities, we told the different physical quantities are there, and when we measure a physical quantity, we need to express it in with units. Now, physical quantities are two types. What are they? Fundamental physical quantity and derived physical quantities. So, fundamental and derived quantities. What are fundamental quantities? That is what first we need to check. Fundamental means, the word meaning itself means basic, fundamental, elementary physical quantities. So with what respect we are telling fundamental here in this context means elementary physical quantities which do not require, which do not need any other physical quantities to express it, or it cannot be resolved further in terms of other units. I'll give an example here. I'm taking density. Density is not fundamental physical quantity. You all know how we calculate density, isn't it? Density is equal to mass by volume. So to express density, it depends mass and volume. If mass alone, if you are measuring, you will not get density. Volume alone, if you are measuring, you will not get density. So to get density, you need to know mass as well as volume. It depends on other physical quantities, right? So density is not a fundamental physical quantity. So, but is there any other quantities which do not depend on other physical quantities? Yes, there are. We will check that. So there are such quantities which do not depend on any other physical quantities. These are length, mass, time, electric current, temperature, luminous intensity, and amount of substance. So these quantities which do not depend on other quantities, other physical quantities. If you want to measure length, you will go and measure directly the length. It does not depend on any other physical quantities. If you want to measure mass, you can directly measure mass. It only mass. It does not depend on other physical quantities. Such quantities are called as fundamental physical quantities. So there are 7 such fundamental physical quantities. Now, what about its units? Length. These are the 7 fundamental physical quantities. Length, meter, mass, kilogram, time, second, electric current, ampere, temperature, Kelvin, luminous intensity, candela, and amount of substance is mole, M-O-L-E. So these are the fundamental physical quantities, these 7 fundamental physical quantities, and these are the units. These units we call it as fundamental units. Fundamental units. I have another table. So these are the physical quantities. These are the physical quantities, fundamental physical quantities, and these are the fundamental units. Units of fundamental physical quantities are called fundamental units. I have to tell 2 things here. That is, when we express the units in words, we need to write it in small letters. Even if these are the units which commemorate the great scientists like Kelvin, ampere and all, to commemorate the great physicist Lord Kelvin and Andre Marie Ampere, we are using these units, Kelvin and ampere. But here we are writing in small letters. But when we come to the symbol, as it what indicates name of a scientist, it should be expressed with a capital letter. The first letter should be capital. Okay, so in this case now, otherwise all the units when we write in words, it should be written with a small letter. Okay, now next is, sometimes we do express units in plural. That is wrong. Example, I can tell you, you may tell sometimes 100 kilometers. That is wrong. 100 kilometer, singular form of unit is enough. Now need to use plural form. 10 seconds, that is wrong. Seconds is not required. 10 second is enough. Okay, hope it's clear to you. So these are the fundamental quantities and the fundamental units. Next is supplementary physical quantities. So these two physical quantities, that is plane angle and solid angle, we didn't add in the previous 7 physical quantities because these two are fundamental, but it is dimensionless quantities. Then you may be asking, like, there are other dimensionless quantities, isn't it? Why these two are so special? This is not only dimensionless quantities, but a purely geometrical quantities. That is why it stands alone. Plane angle and a solid angle. These are called supplementary physical quantities. So 7 fundamental and 2 supplementary physical quantities are there altogether. Now its unit is radian for plane angle and steradian for solid angle. Now what is this plane angle and solid angle, you may be thinking, isn't it? So first we will just to have an idea of plane angle. You all know a circle will have a radius r. We can just express it as radius r, and you just consider an angle in such a way that it is subtended to the center of the circle by these two radii, and in such a way that the angle is formed with the help of an arc that is of length r. Or if you can consider an arc of length same as that of the radius, then this angle theta is called 1 radian. 1 radian. So you all know how angle and arc and radius are related. Angle is equal to arc by radius. So 1 radian means it's a supplementary unit. 1 radian means it is a plane angle. Plane angle means 2-dimensional angle. Just imagine a 2-dimensional angle, a circle you are drawing on a paper, and the angle formed subtended by 2 radii on towards the center, and such that for the arc of radius length equal to the radius. So 1 radian is the plane angle subtended at the center of the circle by an arc of length equal to radius of the circle. So this is the arc. Arc is having the length which is equal to the radius of the circle. In that case, this angle is 1 radian. So that is about plane angle and its unit radian. Now what is solid angle? Solid angle means a 3-dimensional angle. So 3-dimensional means instead of circle you need to imagine a sphere. So in a sphere also has radius, right? So in a sphere, if you could take an area element, and that area element should have a peculiarity, that is, it is the area of that will be equal to square of the radius. So it need not be circle itself. You can have a square shaped area element also, but the thing is that it should be the area should be square of the radius. Then the angle subtended will be if it is satisfying this criteria, that is, area is square of the radius, r square. Then the angle subtended, we call it as 1 steradian. This angle we call it as 1 steradian, alpha 1 steradian here also. Sometimes when we go to buy watermelon from the seller near the street and all, sometimes we will ask whether it is sweeter or not. Then that time they may cut a small piece on the watermelon and dig the knife into that, and they will take out a cone shaped piece out of it, isn't it? So that's called the solid angle, three-dimensional angle. Now if suppose imagine the seller has cut a small area which is equal to the radius of the fruit or watermelon what we have asked for, then in that case this angle subtended will be what called as 1 steradian. So there is a slight difference only between these two definitions, radian and steradian. So radian is a plane angle, steradian is a solid angle. Solid angle. So plane angle means two-dimensional angle. Solid angle means three-dimensional angle. And plane angle, it is subtended to the center of the circle by an arc. Here it is subtended to the center of the sphere, not circle. It is three-dimensional. No? To the center of the circle, not by an arc, by an area element. Here arc of length equal to radius. Here area of area equal to square of the radius. Hope it's clear. This plane angle and solid angle. Okay, so next, derived physical quantities. Now all other physical quantities other than this basic physical quantities or fundamental physical quantities, we call it as derived physical quantities, and its units are called as derived units. It's so simple. Okay, so we will go with an example. You all know that distance is not a derived physical quantity, it is a fundamental physical quantity. Distance means length, path length or length. Time, it is again a fundamental physical quantity. But what about speed? How do we get speed? Speed is distance by time, distance divided by time. So this depending upon the speed is a derived physical quantity. It has been derived from fundamental physical quantities, distance and time, or length and time. So it is a derived physical quantity, and the unit of speed you all know, meter per second. It is a derived unit. Okay. Now there are so many examples like velocity, displacement by time. So velocity is a derived physical quantity. It's a unit meter per second. It is a derived unit. Same way force. It is a derived physical quantity. Mass into acceleration is force and unit kilogram meter square, or we can express it as Newton. All these are derived physical quantities and derived units. Units of derived physical quantities are called derived units. Here acceleration, again it is a derived physical quantity. Mass is a fundamental physical quantity. Acceleration is rate of change of velocity, isn't it? Velocity again a derived physical quantity. So acceleration is a derived physical quantity. Mass is a fundamental physical quantity, and force is a derived physical quantity. Same way density, we already discussed this. We took density as the example to start with about the type of physical quantity. So in density, it is mass divided by volume. Mass divided by volume. So density is a derived physical quantity, and the unit is kilogram meter per meter cube. So volume again a derived physical quantity only, because volume is length into length into length. It is taken from or extracted from where? From the fundamental physical quantity. So all these are examples for derived physical quantities. Hope it's clear to you, this topic. Thank you so much.